So my screen is visible, right?
Yes, sir.
Okay. So I am Chanda Devnath. I am pursuing my PhD at ISER Badhampur. So I am into this PMRF program. I qualified my PMRF in 2022. So I am a TA of this course, this Mechanisms in Organic Chemistry, instructed by Professor Nandita Madhavan. So here in this class I will discuss some of the questions based on this topic, which will help you to solve the upcoming assignments and also the assignments which is already given, the assignment 1. So I haven't, and I have solved some questions from the assignment 0 also, because they have provided the answers already, but haven't discussed the why we are getting that answer. So I have included those questions also here, and I have included some related type of questions which may help you to solve the assignment 1 and assignment 2. So let's start. If you have any doubt, you can ask me during this. I will try to as much as I can. So first we are going to discuss about aromaticity. So you all know about aromaticity from our school +2. So which are called aromatic compound. According to Huckel's rule, the compounds which are planar, fully conjugated, monocyclic system and having 4n+2 pi electrons in a closed shell system, those are called aromatic compound. And if some compound have all these three features, if any compound having all these three features except this one, that is called anti-aromatic. That is, if a compound has 4n electron system, 4n pi electron system with these three features, that we called an anti-aromatic system. Here I have shown some of the examples. So if you see, just let's solve together. So this is a system with one pi bond. You know what is sigma bond and pi bond? Any single bond is called sigma bond. Any single bond is called a sigma bond. If there is only a single bond, if there is only a single bond, then that means that is a sigma bond. Sorry because of my pen is not working right now, so that's why I have to use my cursor. From next class it will be okay. So if there is any bond other than this sigma bond, that is called pi bond. So if there is two bond, first bond will be sigma bond and second bond will be a pi bond. If there is three bond even, so if there is a single bond, that will be a sigma bond. If there is a double bond, one will be sigma, another will be pi bond. If there is three bonds, then one will be sigma and another two will be pi bond. Okay, so this is simple. Now here how, and one bond equal to 2 electron. Any bond, one bond contains, in this type of aromatic system, 2 electron. One bond means 2 electron. Okay. So here how many pi bonds? So if there is 1 pi bond, then that means 2 pi electron. If there is 1 pi bond, that means 2 pi electron. That is clear. So now let's count how many pi bonds are there. 1, 2, 3, 4. So there is 4 pi electrons. So 4 pi bonds. So how many pi electrons? It has 8 pi electrons. 1 pi bond means 2 electrons. So that means 4 pi bonds equals to 8 pi electron. So if you want to get this 8 by this formula, can you get this 8? If n equals to 0, it will be 6. It will be 2. If n equal to 1, it will be 6. If n equal to 2, it will be 10. It will be 10. But there is no formula by which you can get 8 by this formula. So this is not aromatic. This is not aromatic. So this will be a non-aromatic compound. This is not aromatic because it has 8 pi electron. It doesn't goes to this formula, that is 4n plus 2 pi electron. Now next is this one. Now 1 negative charge equal to 2 electron. 1 negative charge means 2 electron. 1 negative charge equals to 2 electrons. So how many electrons are there in this system? Pi bonds 2 electrons. So it will be 4 pi electron. 1, 2. Then that will be 4 pi electron. So that is also not in this formula because you will not get 4 by this formula. If n equal to 0, it will be 2, not 4. So this is also a anti-aromatic compound. And why it is anti-aromatic? As I said, if some compound has 4n pi electron, then that will be a anti-aromatic. So it is a 4 pi electron, it is not aromatic, it will be anti-aromatic. Next is this one. This is, so there is a positive charge, that is there is a no electron is there. There is a scarcity of electrons, so it will not be counted. So how many electrons are there? There are only a pi bond, that means 2 electrons. So that means 2 pi electron. So if you see in this formula, if we n equal to 0, then how many electron will get? 2. So this is a aromatic compound. This is a aromatic compound. Similarly, it has 3 pi electrons, that means it is a 6 pi electrons. So it will be a aromatic compound where n equal to 1. Next is this one. How many pi electrons are there? 3. So it is 6 and this is positive. There is no contribution. So it will be also 6 pi electron. So it will be also an aromatic compound. Next is this one. It has how many pi electron? 4. So it is not 4. Whenever it is 4 pi electron, that will be anti-aromatic. As I said, whenever it is 4 pi electron, it will be anti-aromatic. Next is this one. It has 1, 2, 3. So it also has 4 pi electrons. So this is aromatic. Next is this one. It has 6 pi electrons because it looks like benzene. But if you see this is conjugated with this system. This is another pi electron. So its totally is 8 pi electron. So if it's 8 pi electron, the complete system is not aromatic. This part is aromatic, but you have to consider the complete system. The complete system is not aromatic. Now, if you to be a aromatic completely, all the part of the compound has to be aromatic. On the next problem, you will get it clear. Here you can see, if you see this separately, there are 3 benzene rings. So this is aromatic. This system is aromatic. This system is aromatic because 6 pi like this one. And the in between system, if you know, these pi bonds are delocalized. They are not fixed in at this position. So if you this pi bond can come here, this pi bond can be delocalized at this position. So this middle ring already has one pi bond and two pi bond form each of this ring, because these pi electrons are delocalizing, so it can take 2 electron from this one and 2 electron from this one, so and 2 electron from itself. So all these 3 rings are aromatic. And if you count it separately also, 1 2 3 4 5 6, 6 means 12 pi electron. Not 6, sorry, 1 2 3 4 5 6 7, so 14 pi electron. This 14 pi electron. This is 14 pi electron. If n equal to 3, 3 4s are 12 and plus 2, 14. So this is aromatic. This is aromatic. Okay. So just by counting the number of pi electron, we can select that which is aromatic and which is not aromatic. Now here I have shown 2 extra examples, which by counting the number of electron you may think this is aromatic. See, 1 2 3 4 5. 5 means 10 pi electron. If n equals to 2, then you will get 10 pi electron. Still, so it should be aromatic. According to the Huckel's rule, it should be aromatic because it has 10 pi electron. But this compound is not aromatic because of this structure. If you see the structure of this molecule, all the double bonds are cis. You know about Z or anti, like if both the bonds are at the same side, all the bonds are cis, all the bonds at the same side, they are not anti to each other. So all the bonds are cis, all the bonds are cis to each other. Because of this structure, because of this cis arrangement, this compound, this molecule cannot be planar. And according to Huckel's rule, the compound should be planar. This benzene ring is planar. Planar means you can, it's like a paper. It's like a paper. Planar means if you imagine a paper, you are keeping a paper on a floor. How it will stay? It will stay like a plain compound. So it's like a paper. This compound is like a paper. It's like a page you are keeping on a floor. So it is planar. But if you crush the page, then it will be some wrinkles, so it will be not planar anymore, it will be not a plain straight anymore. Then some part will be above the floor, some part will be in alignment with the floor. So that's why as all the bonds are cis to each other, so this is a kind of strain structure. So if we try to draw this one, it will be kind of this type of structure. Sorry. Kind of this type of structure, which is not I missed one bond, I guess. Anyway, this will be this type of structure, which is not in plane, That's why this is not aromatic in nature. Now if you see the next one, here you can see all the double bonds are not cis. Here this is trans, here this is cis, trans, cis, trans, trans, and this is cis. So here the bonds are mixture of cis and trans, mixture of cis and trans. Because of that, this compound can be stay in the plane. That's why it can be planar. Because of that, it is aromatic. Because of that, it is aromatic. As its compound can be stays as planar. See the orange colored this part, this system can be stayed in plane. So let's solve some of the question which is based on this aromaticity. Let's try. I will just give 1 minute and just give a look and try to sort that which one will be aromatic and which one will be not. I will just give 1 minute. Then I will solve for you. Remember, we have 3 rules. Planar, fully conjugated, that means the pi bond should be conjugated. Here you can see this pi bond comes here, because this can come here, this can come here. So it's totally fully conjugated. So pi bond should be conjugated, and it should have a 4n plus 2 pi electron system. So see which one have this type of system.
Aromatic. Aromatic.
Yes, Rajan has answered. Okay, let's start. So this is a furan system. This is called, it has a common name. This is called furan. So if we count the electron, Rajan is saying 1, 4, 5, 6, 8 and 10. Let's see. Let's solve one by one. Then we'll check how many. So if you see, for this one, 2 pi bonds, so that will be 4 pi electron, and the sulfur has a lone pair, so this can be involved in this system. So it can come here, this can go here. So this way, it can be conjugated with each. If we draw each of the resonating structure, it will be like this. As sulfur is giving us lone pair, so it will be positively charged. Then it will go here. the last one will be, if it goes here, we get back our this initial one. We get back our initial structure. Understood? So that's why it is the lone pairs, the electrons are fully conjugated and the number of electron is, pi electron is 4, satisfy the 4n plus 2 rule, and its number of pi electron is 6. So this is aromatic. So this will be aromatic. Second is this one. You can see how many pi electron? 1, 2, 4. 4 pi electron. So 4 pi electron, it will not be aromatic. So this is not aromatic. This one, it negative charge means 2 electron. So 2 plus 2, it will be 4 pi electron. It will be a 4 pi electron. So that it is also not aromatic. Then this pyridine. Pyridine, if you consider the lone pair of the nitrogen, then it will be 8 pi electron. But if you don't consider the lone pair of nitrogen, it will be 6 pi electron. So here the nitrogen lone pair will not involve in the conjugation. The nitrogen lone pair will not be involved in the conjugation. Only this pi bond will move. So this pi bond will come here. This pi bond will come here. So this pi bond will be only conjugated. So the nitrogen lone pair will be on the nitrogen only. It won't be delocalized. Like this, one student is like 3 of the students are moving in the class, but one student is staying in his place. So here is the nitrogen lone pair is that student. She is staying in its own place. It's not moving. So it is also a 6 pi electron. So you will just consider the electrons which are delocalized. So nitrogen will not be considered. So it has 6 pi electrons. So this will be aromatic. Next is this pyrrole system. In this pyrrole system, this nitrogen lone pair will get involved. So this will go here. It's like a thiophenol type of system. It's like this thiophenol type of system. And this go here. So this is also a 6 pi electron and it is aromatic. Next is this one. Here you can see there is no pi bond. So this is this. If we consider this compound, this compound is not conjugated because there is no pi bond. Both the nitrogen has lone pair, but it can't. This nitrogen has no vacant orbital, so this lone pair can't be shared to this nitrogen. Okay, understood? If there is pi bond, then there is a chance of delocalization because the pi bond is moving here, so this carbon is getting electron deficient. That's why it's taking lone pair of the sulfur. Understood, na? This pi bond is moving this position. That's why this carbon is getting electron deficient. That's why it's taking the lone pair of the nitrogen. But here, beside this nitrogen, there is another nitrogen. It has no vacant orbital to take the proton, the electron from the another nitrogen. So this electron can't be moved to this position. So this system is not conjugated. So it will be not aromatic. Next is this one. It has how many pi electron? 4 pi electrons. So this is not aromatic. This one, this is similar to this pyrrole system. Just instead of hydrogen, there is a negative center. So this will be also aromatic because of the 6 pi electron. So this is also aromatic. This has how many electron? 2 pi electron. But it is a 2 pi electron. It can be aromatic, but it is not conjugated because to be conjugated, you have this electron deficiency on this carbon. Otherwise, how can it take electron from this bond? It can't take electron from this bond because there is no electron deficiency. It has no deficiency of electron. Why it will take first from somewhere else? So that's why the system is not conjugated. So that's why it is not aromatic. This is not aromatic. And similarly for this one, it is similar to the pyridine. The oxygen lone pair will not get involved. This only the 6 pi electron which will move around. So this is also aromatic. So the answer is 1, 4, 5, 8 and 10. Okay. Many of you has answered correctly. 1, 4, 8, 10. 1, 4, 8, 1, 4, 5, 8 and 10. Whoever has answered good. So let's go to our next slides. Here I have shown whatever I have told here, that this nitrogen lone pair is not getting involved in this conjugation. How can you believe me? I can say anything, right? You have to have a proof to say something, that we are imagining that nitrogen lone pair is not getting involved because the pi bonds are moving each other. But there should be some proof. You can't believe my words. So here is the proof. If there is an electron potential map, when scientists check the electron density around this pyridine system, they have seen that there is a yellow or red colored is locked in. See, all this colored, all these different type of color are delocalized in all the carbon, delocalized in all the center. But this only one color is localized to this center. It represents that the nitrogen lone pair is localized in this case of pyridine. See, this is the proof that by in case of electrostatic potential map, you can see that the nitrogen lone pair is getting locked on the nitrogen. It's not getting moved through along the ring. So the next is but if you, in case of pyrrole, I have said that in case of pyrrole, this nitrogen getting involved by this type of, as I shown in case of thiophenes or some thiophenes, that this will come here, and so this is the proof that nitrogen lone pair is get involved in this case. See, this red color is diffused in whole the system. So it proves that the nitrogen lone pair is delocalized in all the carbon. Okay, but here the red color is just on this specific center, but here it is inside the ring. That means it gets diffused throughout the ring. This blue color represents the nitrogen and all the yellow color represent the carbon, and white one is the hydrogen. Next, so this one of the problem which was given in assignment 0 by NPTEL. So I think many of you has already solved, but I will just explain why we are getting that plane. So they have asked for the correct order of acidity for the etalized hydrogen for following compounds. So etalized hydrogen means this one. Correct order of acidity means which will give the H plus in a faster rate. Which will give H plus in a faster rate. Among these three compounds, which will give the order of giving H plus of this compound. So I have already discussed about the aromaticity. So as a hint, I can say that it will be based on aromaticity. I just give 5 seconds because it is already in the assignment, but they haven't give the explanation. So here I am showing the explanation. Okay. Yes, correct. Rajan and Vanshika, Logeshwari, everyone answered correctly. So let's try to solve this one for others. So after removing one H plus, if you are taking a H plus, there will be a negative center on that carbon because you are taking H plus. So H plus is removing, it is giving its proton, it is giving its electron to the system and it is leaving the system. Like it's giving all its books to someone else and it's leaving the class. So if we remove H plus from this system, so I am just showing minus H plus. So what will you get? We will get this type of carbon ion. I am not drawing all the CF3, just imagine it has all the CF3. Okay, and if we remove the H plus, we will get this one. Now, as we know about aromaticity and all. So, among these three, which are aromatic? This one and this one, and both of them has 6 pi electron. So, formation of this, as these carbon ions are aromatic compounds are always stable than that of the non-aromatic compound or anti-aromatic compound. So, it has greater stability, and to form any stable things, the rate will be always faster. Because if you are making something stable, the rate will be always faster. If you are doing something, because the formation of this compound is, if you know about the energy cycle or something, the stability of the compound is very high. So the reaction goes forward. Now, so the lowest rate will be this one because it has 4 pi electrons, so this is anti-aromatic. So the lowest rate will be B. Now among these two, which one will be greater? See, it has a CF3. So CF3 has a minus I effect. Because of that, it can stabilize this negative center. It is already stable because of this aromaticity, and it can also pull the electron from the ring. It can also pull electron from the ring because this electron is delocalizing throughout the ring, and it can pull the electron to itself and get, if some substrate is negatively charged, that is not stable, right? If you pull the electron from itself, it will get some stability. So the highest will be, but it has no such stability. Rather than this methyl will pull electron, methyl will push electron to the system, towards the system. Because methyl has a plus I effect, that is inductive effect, plus I effect, that is an inductive effect, and it has a minus I effect. So it will pull the electron, but it will push the electron. So the highest will be A, then C, then B. Okay. Now the next topic we will discuss, that is resonance and hyperconjugation. Resonance, now you know about the aromaticity, that how the pi electrons move throughout the ring, that is called resonance. Whoever has better movement of electron, that is better resonance, that system is more stable. Now what is resonance? Resonance is the stabilizing of a molecule through delocalization of the bonding electron in a pi orbital. So the pi bonding electron will move throughout the system, and the molecule gets some stability. The most stable form of a molecule, and what will be the criteria of this resonance? you see, this is a phenol system. I have shown the resonating structure of this one. How it goes? They have gave this electron comes here and it moves in this position. Then when we get this structure, the next one, this negative charge goes here, here, and the next one, this comes here, and then goes here, it comes here, and we will get back our first structure. Now among these four, which structure is now all these four structure should be like that way that it can show all the possible structure of the molecule, and resonating structure have the same number of electron and molecular formula. See, if you consider this one, how many pi electron is there? There is 6 pi electron, and this total 6 pi electron in the ring, and if you consider the oxygen, then it is total 8 pi electron if you consider the lone pair of the oxygen. But so how many electron will be in the ring? 6. So if you count the ring, the negative charge means 2 electron and 2 pi, so it is also 6 pi electron. And on oxygen has 2 lone pair. Oxygen has 2 lone pair. Okay. So now it has 1 lone pair but 1 pi bond. So oxygen has also 2. Sorry, yes, 4 pi electron. Pi electron actually. Just consider the number of electrons, that will be better. So this ring has 6 pi electron. This ring has also 6 pi electron. This ring 4, 1, 2, 3, 6 pi electron. This ring 1, 2, 3, 6 pi electron. Now consider the oxygen. Oxygen has 2 lone pair. So 4 electron. 1 lone pair, 1 pi bond. 4 electron. 1 lone pair, 1 pi bond. 4 electron, 1 lone pair, 1 pi bond. So all the structures should have same number of electrons and molecular formula. So see, the molecular formula is also same. Oxygen, nitrogen, 3 carbon. Oxygen, nitrogen, 6 carbon. Oxygen, nitrogen, 6 carbon. So the molecular formula is also same. And the hybridization of the atom in the molecule should also be same. See, all these carbons are sp2 hybridized. In this case also sp2 hybridized, sp2 hybridized, sp2 hybridized. Which is called sp2 hybridized if a carbon has 2 sigma bond and 1 pi bond, that is called sp2. 2 sigma bond, 1 pi bond, that is called sp2. So here all the carbons are sp2. So these are the criteria of resonance. So if you are doing some resonance, you have to see that after drawing all the resonating structure, all the compounds should have same formula, same number of electrons and hybridization. Here I have shown another resonating structure. This is acetic acid. Where this lone pair comes here, and so here both the structure are equivalent because both the resonating structure is same, so it's equivalent. So let's now draw the resonance structure of the following compounds. You don't have to send the answer, just try to solve, imagine and solve it by you. I'll just give 10 seconds. Okay, let's start. So this is just a phenol which I have already shown. This is a phenol system. So here you can see. So how it will go? The oxygen lone pair will come. This oxygen lone pair will come here. It will go here. It will be negative charge. The lone pair goes here. similarly. So it is the all the resonating structure of this phenol. Now what is this one? This is a benzylic cation. This is a benzylic cation. If we draw this one, it will be like this one. C6H5 means there will be a benzene ring. Whenever you are seeing something C6H5, it is usually benzene ring. And there is a CH2, and CH2 is plus. Why plus? Because carbon can form how many bonds? 4 bonds. But here it's forming 3 bonds. 2 CH2 and 1 this carbon. So our carbon has a deficiency of bonding. So that's why it will be positive. So now you have to show the resonating structure of these compounds. It will be like similar to this one. But here, as the oxygen has electron, so it's giving the electron. But it has already the scarcity of electron. So the movement of electron will be which side? This side. Because it has no electron to give to this ring, towards this ring. So movement of electron will be opposite side. So here is the structure. Where you can see the movement of electron will be this position. The pi bond will move here. There will be electron deficiency. Then this pi bond will come here. There will be an electron deficiency. Then this is all the conjugated resonating structure of this benzylic cation. Okay, I think it's clear. Then try to solve our next question. How many resonating structure will have N3 minus? N3 minus. This is triazole anion. You know N3 minus means 3 nitrogen. It is there is a problem in this. It will not like this. It will be like this. N3 minus. They have, instead of superscripting it, they have just, it will be N. N3 minus. Obviously N3 minus is like, it will be like normal nitrogen. N3 minus will be like normal nitrogen. So it will be N subscript N3 minus. So this type of structure. So how will you show the resonating structure? So if we draw the normal structure, this is the basic structure. So you have to show the resonating structure of this compound. So here I have shown. So here whatever this is, this one 5 minus 2, because nitrogen always form 3 bonds. Nitrogen always form 3 bonds. But this nitrogen can form 3 bonds. Like oxygen can form 2 bonds. Carbon can form 4 bonds. So nitrogen can form 3 bonds. So here this nitrogen is forming 3 bonds, so this is neutral. This nitrogen is forming 4 bonds. More than it can form. So there is a scarcity of it. It has given whatever it had. Its capability is to form 3 bonds, but it's doing more than its capability. So it has some scarcity. So it is positively charged. But this nitrogen should form 3 bonds, but it's forming 1 bond. So it has efficiency of 2 bonds. It has already electron to itself. It can form those 2 bonds, but it's not forming. So it has an efficiency that will be 2 negative. Whenever there is scarcity, it will be positive. So nitrogen 4 bond, it has scarcity because it has done more than it can do. It can form 3 bond, but it's forming 4. So 1 bond extra. So that's why 1 plus. Then this nitrogen can form 3 bond, but it's forming one bond, so 2 bonds less, so that's why 2 negative. So this is the structure. If we show the resonating structure, what will be the resonating structure? If it gives one of the electron to this one and this moves here, then you will get this structure where these 2 nitrogens are negatively charged because it has given 1 electron. So 1 negative it has given, so it will be 1 negative, and it's still 4 bonds, so it will be positive. Now it has 1 scarcity of bond, so that is negative, so it is 2 negative, and still another probability is if it gives another electron and it goes here, then we will get this structure. Okay, so these 3. So how many resonating structures are possible? The answer will be 3. So how many resonating structures are possible? No. That is not 2, it will be 3. See? 3 is the right answer. Okay? If anyone haven't seen this type of compound, you can draw this 3 structure. You have understood, right? How this negative charge is moving? It has minus 2, so it's giving 1 electron, so it will be minus now, and it's taking 1 electron, so it will be negatively charged. Now it's taking another 5 bonds, so it will be minus 2 now, and it's giving whatever it has, so it will be 3 bonds, so it will be neutralized. But in all the 3 structures, this nitrogen has 4 bonds, so that's why it will be always positive. Now if someone asks, among these 3 structures, which structure is more contributing? You know about this contribution of resonating structure. Like if a compound has more than one resonating structure, one of the structure contributes to the structure in a greater extent. See, like in this compound, both the resonating structures are same. Both the resonating structures are same. So here both the resonating structures are contributing equally to the actual structure. But in this case, all the 3 resonating structures are not same. These 2 can look like it's similar, but if you mark, this is nitrogen A, this is nitrogen B, or these are like equivalent if you don't mark even. Both the resonating structure are same, these 2. So this will contribute equally. But this resonating structure looks different. So which will contribute more? Here, in case of resonance, there are some rule to determine. One second. To determine which is more contributing. So one of the rule is the charge should be in the structure where the charge is more delocalized, that structure is more stable. So what does it mean? The structure in which the charge is more delocalized, is not on a specific atom, it is more delocalized throughout the molecule, that structure contributes more than that of the other structure. So here you can see, in this structure the charge is only localized on these 2 nitrogen. This nitrogen is neutral. Similarly, in this case also, this nitrogen is neutral. This charge is just localized on these 2 nitrogen. But here all the nitrogens are charged. So the charge is delocalized in all the 3 nitrogen. So that's why this structure will be more contributing. Understood? The structure 1 will be more contributing because any structure where the charge is more delocalized, that structure will be more contributing. So based on that, I think from this concept you can answer one question from assignment 1. You will go and check. I think now you can answer. I think question number 1. They have, in that one also they have, or I don't remember the question number, but it is in assignment 1. They have also asked about which one is the more contributing structure. So what is the rule in the structure where the charge is more delocalized, where now the charge is not closer to each other, the charge are separate to each other, that will be more contributing. If you have some type of structure, I am just giving an example. If you have some structure where the positive charge is here and the negative charge is here, and if you have some structure where the negative charge is here and the positive charge is here, which one is more stabilized? This one, because here the charge is more delocalized, the charges are separate to each other, so there is less diffraction among the charge. If you can, so where the charge are more delocalized, that is the electrons movement are more, that will be more stabilized. Based on this you can answer one question, I think, in assignment 2. Go today and go check. So this is also an question from assignment 0. So they have asked for the resonance structure of these compounds. Is or are, that is, it can be more than one. Answer could be more than one. So this one you can answer now, I think. Just try. I'll just give 5 seconds. Okay, let's solve. So the resonating structure will be conjugating. So if this electron comes here, this bond goes here, goes here. So which structure we will get? We will get this one. See, this bond is coming here, this pi electron is coming here, this bond is coming in this position. So this will be one of the answer. Another, so there is a probability of more than one answer. So you have just, whenever there is a is or are, you have to check if there is any other option is available or not. So if you look into this position, here they have delocalized the negative charge in this position. It is not possible. Negative charge can't go on this position because there is no conjugation at this position. It can't jump from this center to this. It is not possible. So it will be not our answer. Next is this one. Here what they have shown. So if I just count the number, 1, 2, 3. That is 1, 2, 3. So what they have done? They have just shifted the negative charge from 3 position to 2 position. That is not a conjugation. How can it be possible? It's not possible, right? Just you can't shift one negative charge to this position. You have to be some conjugation by which. So this is not also our answer. This is not possible. Next is this one. If you just stop our movement of electron, if we just stop our movement of electron at this position. Then we will see, we will get this structure. This pi bond will shift here, but this pi bond, instead of go this side, will be at the negative charge. Then we get this one as our structure. So which will be our answer? No, not a 1 and 4, not 1, 3, 4. It will be 1 and 4. Understood, right? 2, it can't be 2 because negative charge can't go from this side to this side. There is no conjugation. And here they have just shifted the negative charge from 3 to 2. From 3 to 2. It will look same. That's why always whenever there is an open chain system with a lots of carbon and you are getting confused by just looking at them that it is the negative charge has moved or not, just give the numbering. See, if you are giving the numbering, that is simple now. This 1, 2, 3, 1, 2, 3. So negative charge is getting shifted from 3 position to 2 position, 3 position to 2 position. So that is not possible. So it is not a resonating structure. So Vanshika and Rajan has answered correctly. Good. Tejaswini, 3 is not correct because if you give a numbering, you can see it's not correct. And 2 is also not possible. Okay. So let's go to our next topic, that is what is hyperconjugation. So now you know about the resonance. So this is the one type of resonance. This is also called as a no bond resonance. This is also called as a no bond resonance. So what is hyperconjugation? In case of resonance, we just look into the movement of a pi electron or lone pair of electron. But in case of hyperconjugation, you can shift the bonding electron also. So hyperconjugation is the stabilization effect on a molecule due to interaction between a sigma bond and a pi bond. So in case of resonance, we are just showing the movement of, as you have seen, in case of resonance, we are just showing the movement of pi electron. The sigma bonds are fixed. The pi bonds are getting moved from one place to another place. But in case of, it's looking too bad. But in case of hyperconjugation, a sigma bond can also get involved in this conjugation. So let's see what are the criteria of this. The sigma orbital will interact with an adjacent empty pi orbital. So here you can see this is sigma bond, this CH bond get involved with this empty pi orbital of the adjacent carbon. Usually the overlapping of the bonding electrons is CH sigma bond and 2p or pi electron of the adjacent carbon. So here this CH sigma bond get involved in this pi electron, with this empty pi electron. And due to this hyperconjugation, what is the result? It causes the length of the sigma bond to be reduced and the length of the pi bond to be increased. Due to this conjugation, the pi electron gets the length of this sigma bond get reduced, and if you show in this type of system also, like I will show later, if this type of system is there, in that case the pi bond length get increased and this sigma bond length get reduced. Moreover, it helps to increase the stability of the carbocation. And by this hydrogen removal, we are forming a carb anion, because carbon contains an anion, and carbocation is this one. This is called a carbocation. So by hyperconjugation, a carbocation gets a stability. So here I have shown some example. So this is a methyl carbocation. This is a propyl carbocation, because 3 carbon means propyl. This is also a propyl carbocation, but it's a secondary, and this is a tertiary butyl carbocation. Now this carbon has no adjacent carbon, so there is no such hyperconjugation effect, because hyperconjugation happens between CH bond and their adjacent vacant p orbital. Here this plus is on this is carbon, but it has a adjacent 1 carbon, so this is showing as a primary. This is the number of the carbon atom, number of the adjacent carbon atom. So it has 1 adjacent carbon atom, so it is primary. It has 2 adjacent carbon atom, which is secondary. It has 3 adjacent carbon atom, so it is tertiary. So if you see how many adjacent CH bonds are there, that is 2. It's called, if you say this is alpha position, so how many alpha CH bond? 2 alpha CH bond. Here 3, so it will be 6 alpha CH bond, and in this case 9. Now, as we have shown by this hyperconjugation structure, this CH bond can get involved, can get resonance, involved in resonance with this vacant p orbital. So this will come here and we will get this type of structure. Okay. Now if another hydrogen move, one possibility is this one, another is there is another hydrogen, so this can also come here and we will get another structure, that is both are similar, but the probability is 2, because there is 2 hydrogen, so the probability is 2. So how many? So if you just count the number of 2 alpha each, the number of alpha CH bond, you can count that how many hyperconjugative structure it will have. So it has 2 hyperconjugative structure. So similarly, it has 6 alpha hydrogen, so it has 6 alpha 6 hyperconjugative structure. It has 9. So if the number of alpha hydrogen increases, stability more resonance means more stability, as I said earlier also. More resonance means more delocalization of electron, so more stability. So stability will get increased. So there is this CH bond electron getting delocalized, so that's why more the number of alpha hydrogen, more is the stability. In case of radical also, you can see this is a methyl radical, there is no alpha hydrogen, so it's 0 alpha hydrogen. It has 3, it has 6, it has 9. So it has 9. So the stability order will be, this will be more stable. And here the alpha hydrogen, if you show this alpha hydrogen like this one, it will move like this one. So in case of radical, you should keep in mind that you have to show a single headed arrow. because you are, in case of normal system, when you are moving a bond, we are moving 2 electrons. But in case of radical system, when you are moving a bond, we are moving 1 electron. So to imply that one, if we are moving 2 electron, we are giving a full headed arrow. But if we are moving 1 electron, we will give a single headed arrow. We will give a single headed arrow. Whenever you are doing any mechanism with, in case of radical, you should show a single headed arrow. A double headed arrow means movement of 2 electrons, but a single headed arrow means a movement of 1 electron. So let's see for this system. So they asked what they asked. Many of you has already answered. So number of hyperconjugation structure of isopropyl radical. What is isopropyl? Propyl means 3. So isopropyl is this structure. Or if I show this one, this is isopropyl. This is isopropyl. Like this one. So how many alpha hydrogens are there? 6. So how many hyperconjugation structure will be there? It will be 6. It will be 6. Many of you has answered already. Everyone has given a correct answer. So it will be 6. So as what we have learned from this one, the number of alpha hydrogen increases, the stability increases. The number of resonating structure increases, stability increases. So whenever there is a delocalization of electron in a greater extent, that will gain more stability. So this is a question from assignment. I will just give 5 seconds. It is also based on this resonance and hyperconjugation. We have to consider both the resonance and hyperconjugation. Try to answer this one. You have to consider both the resonance and hyperconjugation. Just try to solve. Okay, let's try together. So this one is a tertiary carbocation. How many alpha hydrogen it has? It is a methyl, so 3. Another methyl, 3. It has 2 hydrogen. There is a 2 hydrogen. So how many alpha hydrogen total? 8. 8 alpha hydrogen. It has 1, 2. So it has 6 alpha hydrogen. It has now see, in this case It has a resonating stability. It has a resonance stability, but it has no resonance stability, no such resonance stability. So the correct order will be the correct order will be B, A, C. So the correct order will be B, A, C, because it has 6 pi electron. I have some doubt with this question. Answer. So here you can see I don't think this the correct answer will be, so it has 8 pi electron, it has 8 alpha hydrogen, so it has 8 hyperconjugative structure, so it has some greater stability, but both of them have 6 pi electron, 6 alpha hydrogen, so there will be 6 hyperconjugative structure. Now it has a resonating effect of oxygen, but it has a resonating effect of pi bond. So as it has more hyperconjugative structure, this will not be correct answer. It will be the correct answer. So as it has more hyperconjugative structure, so it will be more stable, as alpha hydrogens are 8, and in this case the alpha hydrogens are, sorry, it will be alpha. So, the alpha hydrogens are, so here 6 alpha hydrogen, the 6 alpha hydrogen, so there is 8, that's why it will have 6 hyperconjugative structure due to having more conjugative structure. It has more stability, so the highest stability is this A, then both of them have 6 alpha hydrogen, so both of them have equal stability, but here the resonance stability is getting by the oxygen, so lone pair is more prone to give, the oxygen is more prone to give its oxygen lone pair to this electron deficient center rather than this carbon pi bond, so it has greater stability than B, so the order will be A, C and B. Whoever answered I was just confused by the answers, that's why. It will be the right answer will be A, C, A greater than C greater than B, not the answer B. It will not be the answer, because B has already 6 electron, but 6 alpha hydrogen, but A has 8 alpha hydrogen, so anyway B has less stability than that of the A, because A has 8 alpha hydrogen to give the more hyperconjugative structure. Understood? So it has the stability, it has 8 alpha hydrogen, it has 6 alpha hydrogen with this pi bond resonance, it has 6 alpha hydrogen with this oxygen resonance. So as it has 8 alpha hydrogen, so it is more stable, and among these two, as oxygen lone pair giving probability is greater than than that of this pi bond, so that's why C is more stable than that of B. C is more stable than that of B. So the stability order will be A, C, B. Okay. So let's go to our
Excuse me, ma'am.
yes.
Ma'am, I wanted to ask one thing. Does this mean that hyperconjugation provides more stability as compared to resonance if we are considering 8 alpha hydrogen and 6
Yes,
alpha
if there,
hydrogen here?
because if there is alpha hydrogen is available, then it will give, if it is in case of resonance, if you are getting some aromaticity and all, that will be a different case. But if there is no aromaticity and all, but you are getting alpha hydrogen, hyperconjugation will have more effect because there is a sigma bond which is getting delocalized. So it will give more importance to this structure to get gaining stability in this case.
Okay, thank you, ma'am.
So let's go to our next topic. This is the last one. So the types of reaction mechanism. I think Nandita ma'am has already taught all these things. I am just giving a recap so that you can connect with the upcoming questions. So there are three types of reaction. One is polar, radical, and concerted. Polar means where the positive and negative are reacting with each other. Like one will be electrophilic center, another will be nucleophilic center. One center is electron deficient and another center is electron efficient, and both of them will react. That is called polar. Another is radical. What is radical system? Radical means when two radical, like one electron get combined with each other. That is called radical. And concerted means it's happening in a single step. That there is no such formation of electrophile or nucleophile or any center is electron deficient center is not creating. It is just partially electron deficient, partially electron efficient centers are reacting with each other. They are not forming a proper cation or anion. They are just reacting in a same system. Suppose I will go to the next classes. I will discuss about the concerted, which is concerted. Without example, I can explain, because in case of concerted, there is no formation of a solid positive or negative charge. There is a partial positive or negative charge. They are just coming together in a system and they are reacting. So there are different type of polar reaction, like substitution, elimination, addition, elimination, and elimination, addition. So what is substitution? There are two types of substitution. One is nucleophilic, another is electrophilic. What is nucleophilic? If nucleophile is coming and substituting one group from a system, then that will be called nucleophilic substitution, because nucleophile is coming and substituting that one. And electrophilic substitution means when the electrophile is substituting something from the system. Suppose as you have a benzene ring, okay? If a nucleophile, if you have a benzene ring with any group or any functional group, if any nucleophile comes and substitute that one and insert into it that benzene ring, that will be a nucleophilic substitution. And suppose if a electrophile comes and insert into that benzene ring, that will be electrophilic substitution. Next, this type of nucleophilic substitution are two types. One is SN1, SN2, and there is another type of SNI that is not that much important. Main two are SN1 and SN2. And electrophilic substitution are two types. One is aromatic electrophilic substitution, another is aliphatic electrophilic substitution. It's clear by the name. Aromatic will be in the aromatic system and aliphatic will be in the aliphatic system. Next is elimination. Elimination are two types: syn elimination and anti-elimination. Syn elimination means when the eliminating groups are seen to each other. Seen means both are in the same side of the bond and they are eliminating. Suppose in a class, if two students are living from a same side of the class, then that is seen. If one student is living from the one side and another student is living from the another side, then that will be an anti-elimination. So anti-elimination are three types: E1, E1CV and E2. All this 1 and 2 whatever I have shown, this represents the order of the reaction. Order of the reaction, if you have read about the kinetic theory, you have know about the order of the reaction. Order means whichever the number of molecule or the number of substituent which affect the rate of the reaction. If one substituent affect the rate of the reaction, that will be first order reaction. If two substituents affect the rate of the reaction, that will be second order reaction. So in case of SN1, only one substituent affect the rate of the reaction, and in case of SN2, two substituents affect the rate of the reaction. Similarly in E1, one substituent, E1CV also one, and in case of E2, there's two substituents affect the rate of the reaction. And there are another type of things are like addition, elimination and elimination. All this will be discussed in the upcoming classes. So our today's goal is to explain what is substitution and mainly what is nucleophilic substitution. Here I am discussing what is nucleophilic substitution. When an electron-rich nucleophile selectively binds or attacks the positive or partially positively charged of an atom of group or atom and replace the leaving group, that is called nucleophilic substitution. As I have shown, it has two types, SN1 and SN2. This is SN1, this is SN1 and this is SN2. In case of SN1, this is a stepwise process where this leaving group removed from the system and a carbocation gets generated, and then the nucleophile enters and we get our desired compound. But in case of SN2, the nucleophile attacks and the leaving group removes from the system and we get our desired compound. Understood? In case of so, why in this case it is happening in a stepwise, when the leaving group is leaving from the system and after that the nucleophile is entering. But in this case, both the work is happening in a same single step. So what is SN1 reaction? So it's a unimolecular, stepwise. Carbocation generation is the rate determining step, and rate depends on stability of the carbocation. What I am saying? See, this is a stepwise process. The first one is leaving group is getting removed from the system and generating this carbocation, and then the nucleophile is entering and we are getting this product. Now between these two steps, the first step is the slow step, and according to the kinetic theory, we know whichever is the slow step is the rate determining step. Whichever is the slow step is the rate determining step. Now the number of components which are getting involved in a rate determining step, with that defines the rate of the reaction, or that get involved in the rate law. You know about the rate law? R equals to rate constant now in case of SN1, you can see in this slow step only this substrate is getting involved. The nucleophile is not getting involved in the first step. So the rate law only depends on the substrate. That's why it's called unimolecular or a first order reaction. That is called a first order reaction because it is only one substituent in the order. So the order of the reaction is one, because only one substituent which is involved. Because in this first step, in the slow step, the leaving group, the nucleophile is not involved in this step. So it only depends on the substrate and stability of the carbocation. Because in the slow step, we are generating the carbocation. As much this carbocation is stable, this reaction will be faster, and if the slow step is faster, that means the rate of the reaction is fast. So the rate of the reaction will be higher. So the stability of the carbocation increases, the rate of the reaction increases, because the main path, which is the slowest path. If that is faster, the slow step is faster, then the rate of the reaction will increase. Because this step is not considered for the rate of the reaction, only this step is getting considered. And if you can enhance the rate of this slow step anyhow, then we can enhance the rate of the reaction. That's why if the enhance the stability of the carbocation, we can get more stability rate of the reaction. So as you know, by the hyperconjugation and all, the 3 degree, that is the tertiary carbocations, are more stable. That's why the rate depends on stability of the carbocation. So if it is 3 degree, rate will be higher, 2 degree, then 1 degree. Understood? So there is another question which is from assignment. So the correct order of the given bromide for SN1 reaction. So SN1 means the leaving group will remove from the system. Leaving group will get removed from the system, and it will generate a carbocation. So whichever carbocation will be stable, that will be react in a highest rate. So let's, I think many of you has already solved. Okay. So here, if we remove the bromide from the system, we will get how many pi electron? 2. By this one we will get how many pi electron? 4. So you can see this is a troponium ion, that is 6 pi electron, aromatic. So it will be always this will be aromatic. Okay, so the highest rate will be 3. After that, it has 2 pi electron, it has 4 pi. As it reaches 4 pi, that will be anti-aromatic, so that will be least stable. So the least stable will be 2, and it's not aromatic, but it has 2 pi electron. It can consider as aromatic. It's not aromatic because there is a no. But if you can consider just the stability of the carbocation, it has a stability of this carbocation. So that's why the stability order will be like this: 3, 1, 2. Understood? Why we are considering this one as a faster? Because it is aromatic. Second, this one, why? This, if we just consider this as a allylic system, just allylic cation, because this is not aromatic, there is a no cyclic conjugation. So if we just consider it as a allylic system, it has some stability. But in this case, the carbocation is anti-aromatic. Formation of an anti-aromatic system is highly unstable. It will not get formed. So this, you can't even, this carbocation will not generate in the system. The rate is least means this carbocation will not generate. If you, in a reaction vessel, if you give this one and add some nucleophile, this center will not even generate to react. So that's why this will be our rate of the reaction. Okay, I think it's clear. So this is the last slide of our, this is the almost like there is some extra question. Try to solve. There is no option. You have to draw the product. You can't send me the product, but just try to. It will be, as you see, there is a methanol and bromide. So bromide will get removed from the system and carbocation will generate. Then after that, what will happen? Just try. I will solve it for you. I hope this question will help you to solve some upcoming assignments and also whichever examination you are preparing for. So let's try to solve the first one. This bromide will get removed from the system. As you know, this is methanol. Methanol, this oxygen has lone pair. This is a weak nucleophile. This is not a strong nucleophile. It is a weak nucleophile because oxygen is not negatively charged. If it is not negatively charged, that is weak nucleophile. That weak nucleophile means is not that much faster it will attack. If anything is weak nucleophile, that will go through a SN1. If the nucleophile is strong, that it has negatively charged or something like OH minus or ONE minus, that will go into a SN type of reaction. But if the nucleophile is not charged, then you can get an idea that it will go through a SN1 type of mechanism. So if any reaction is in water or methanol, that usually goes through a SN1 mechanism. Understood? If the nucleophile is not negatively charged, those reaction usually goes through a SN1 type of mechanism. So if any reaction, they are not, you will see in many GATE or NEET question, they are not even giving the nucleophile. They are just mentioning that hydrolysis of the reaction. Hydrolysis means the reaction with water, or they are saying the methylation of the, or not methylation, like or anything like hydrolysis of the reaction. So the reaction is in water. If the reaction is in water, that means that is not negatively charged. So reaction will go through a SN1. If you go through a SN2, then it will get a wrong answer. Understood? So whenever this is hydrolysis or water or methanol, that will go through a SN1 type of mechanism. So let's try to solve this one. So first bromide will remove from the system and we will get our carbocation. Now this carbocation, so this is 3 degree carbocation. This is the highest step. It has highest step because it has 3, 3, 1, 7 alpha hydrogen. And so our product will be this one. And CH3OH. Not OH, CH3OH. Now CH3OH means this part will attack and we will get oxygen will be positively charged because it's giving one proton, one electron. So now, as it is oxygen is positively charged, so we take electron from this hydrogen bond, then H plus will get removed and we'll get this one as our product. So now let's go to our next question. What will happen? Here I have already shown the product. So here it is 4 member, but in the product we are getting 5 member. How is possible? So it's just first remove the lone pair, remove the leaving group. Whenever you are getting this type of system, just remove the leaving group first. Then we will get an idea. So we are forming this one. Now we all know that here why this is ring shifting is not happening in this place, because 5 member rings are stable. 5 and 6 member rings are stable rings. 5 and 6 member rings are stable rings. That we know. Because of that bond angle strain and all. The 5 and 6 member rings are stable. But 3 member rings are not stable. That's why this ring has prone to form a 5 member ring. If it has probability, if it has chance to change itself to a 5 member ring, because it's not stable, it's very fast to change to a 5 member ring. That's why. So, and it is a 2 degree. So this carbocation is not that much stable. Here it was 3 degree. So carbocation was already stable. Here the carbocation is 3 degree. So carbocation is not that much stable. So that's why this bond will shift to this position. Then it will be like carbon-carbon bond shifting. Carbon-carbon bond shift. So it will lead to this type of compound. So now the positive charge is this, because bond is shifting from this position. So this carbon is now vacant, because we are taking electron from this carbon. So this carbon is now electron deficient. So positive charge here is a carbon. So the positive charge will move to this position. Now this carbocation is also 2 degree. So there is another chance, if there is any chance to get a stable carbocation which is 3 degree, it will go that way. So there is a hydrogen atom available. There is a hydrogen atom available. So it will shift this alpha hydrogen. So okay, what will happen? Alpha hydrogen shift. This shift is not hyperconjugation, it's shifting totally. This part of the bond is coming here to this position, it's shifting. So this bond will shift. This carbon hydrogen bond will get shift to this position, and we will get. So the carbocation, this positive charge, this center is electron deficient. So this center will be electron deficient. Understood? So this center will be electron deficient. Now water is in the medium. Now this carbocation is 3 degree plus 5 member. 3 degree plus 5 member. So it is stable now. 3 degree plus 5 member. So it is stable, enough stable. So now this water will get a get our this. Understood? Any doubt? I think it's clear. So here is a bond shape. So whenever that's why it's very important to determine if the reaction is going through a SN1 or SN2, because in case of SN2 there is no chance of rearrangement, because the carbocation is not forming, right? In case of SN2, the leaving group will just go from here and nucleophile will just enter here. So there is no chance of rearrangement in case of SN2, but in case of SN1 there is a chance of rearrangement, that carbocation will rearrange to form the more stable carbocation. So it's very important to determine our reaction is going through SN1 or SN2. So if there is any weak nucleophile, that is methanol or water or any uncharged solvent, that will be a SN1. And if the nucleophile is charged like OH minus or OMe minus or any charged nucleophile, that will be go through a SN2 pathway. Okay. So today's now is almost end to our class. So this is the last question of today. It came in GATE 2019. I added this question so that you can relate that all whatever we are learning by this class will benefit us to solve our gold examination, which is GATE or NET. All these type of questions come with very easy topic, and it's just a one shot and you will get a right answer. So if you can get a right answer of this one, you are getting 1 mark in GATE. So try to solve this one. Amal answered, Rajan answered. Everyone is saying D. Okay, let's see. See, whatever you know, this is here. This is a Grignard compound. This is a Grignard compound. So in case of Grignard, this is negatively charged and magnesium is positively charged. So here the nucleophile is CH3 minus. Here the nucleophile is CH3 minus. So this one will attack to this position and this will open. So we will get CH3 and O minus. Now in medium they have given H plus, so it will take H plus, or HCl means they are giving H plus. Like acid is giving H plus. Any acid they can even write as H plus. They can write even an acid H2SO4. Any acid is giving H plus. So this is what we are getting. Now as we are adding acid, we can't say our reaction that you will just take one proton. You can't take another proton. You can't control that. So if in medium you already have acid, it is very, because oxygen is there, so it will take another proton. You can't stop him that you can't take another proton. You have to take just one proton. You can't stop him. So it will take another proton. By this oxygen lone pair, and this will be OH2 plus this oxygen is giving its lone. So it's a very good living group, because water is a very good living group. We are getting water. That is, water is more stable thing, you know, because around us everything is water. So water is the most stable thing. It will get removed and we will get, sorry, there is a hydrogen. Now I have told already that 4-member rings are not stable. So if there is a chance of shifting, and this is a 2-degree carbocation. 2-degree carbocation has not that much stability. It is 2 degree and with a 4-member ring. So it's very prone to rearrangement. It's very prone to rearrangement. Because it has 2 degree, it has not that much stability in itself to control itself to not to get rearranged. So it's not that much stable, and moreover it contains a 4-member electron, a 4-member ring. So this bond will shift from carbon center will shift here in this position. Now similarly there is a hydrogen like the previous one. So the hydrogen will shift and will form. This hydrogen will shift to this position and will form. So this hydrogen is shifting, so this center is now electron deficient. And when as H plus we have taken, so there is a Cl minus in the system. So this Cl minus will attack to this positive center and get our product. So the answer will be D. So whoever has answered correctly, Rajan, Amol, Sri Vikram, Deepika, Logeshwari and Tejashwini, you can see that it is a 4-member ring. So 4-member ring is not that much stable. So that's why it's very prone to rearrange. Okay? Sorry. Okay. So this much for this class. Anyone has any doubt? Okay, I'll just give a short recap. We started with aromaticity. We have explained aromaticity of different type of compound and how we can prove that nitrogen lone pair is localized. Thank you, Rajan. Then I discussed about resonance, hyperconjugation, shown some example. Then SN1 mechanism and this question. So okay, I think everyone has understood and enjoyed this class. We'll meet in the next class in the next Sunday at the same time. So I will upload this video in YouTube and NPTEL also. I will upload the video already. I don't know how can I send the questions actually. I have to check with the NPTEL how to send these questions. But I will upload the video by NPTEL. You can go through the video and check the questions, and I will upload my slides also there. But how to send the question, I have to talk to the NPTEL. Then I will send this question to all you guys. Thank you everyone. Have a nice day. Enjoy your Sunday. Bye.